Hello, my name is Dan Koditschek. I'm a professor at the Electrical Systems Engineering Department at the University of Pennsylvania. And it's my great pleasure to thank the workshop organizers for inviting me to come and speak to you about the role of topology in robotics. My notion for today's talk is to talk about a recent review article that I've written arguing that robotics is the programming work science, which I am trying to get across with this little energy basin cartoon. And I'm leaning heavily in this article on the famous work by Professor Herbert Simon, who wrote extensively on the sciences of the artificial, who pointed out to us that these synthetic sciences entail a triple wherein an architecture is designed to accomplish a task in an environment. And he argued forcefully that these synthetic systems work well when they work on the basis of hierarchy achieved through modularity depending on robust reuse. So we know that work entails dynamics. Newton made this very clear hundreds of years ago, 300, 400 years ago. And when we study dynamical systems, we come to understand that topology plays a central role in achieving what we continually stub our toes on, which is this signal to symbol gap. And so the use of topology in robotics has to do with its fundamental role in guaranteeing equivalence through conjugacy or change of coordinates, and more recently as shown by Conley's fundamental theorem at the end of the 20th century, that every dynamical system can be decomposed into its attractor basins using notions of chain recurrent sets. So this paper argues that topology bears the relation to robotics that logic bears to computing insofar as we get our gaps healed by the symbols that topology gives us. The caveat here is that the hybrid dynamical systems problem is still wide open. The topology thereof is still pretty open and still quite under development. What I'd like to do in this talk is use a case study wherein we start with very abstract point particle motions, reactive planners for point particles in the horizontal plane. Then we try to instantiate those horizontal plane point particle dynamics with sagittal plane mechanisms, legged mechanisms, whose sagittal plane organization is critical to achieving that horizontal plane motion. And finally, the hierarchy forces us to develop joint level controllers that support these sagittal plane arrangements of pieces of body. So these ideas can be formalized, again, using ideas from topology to show that reuse via conjugacy or recombination in sequence or in hierarchy or in parallel have formal properties. And there's a growing empirical track record that begins to suggest that these compositions lend themselves to programming. Most recently, I'll end with a brief account of some new theoretical advances that begin to put the meat onto the bones of this skeleton, that these recombination methods can actually be turned into formal programming languages. So that's my plan for the talk, and we'll now move ahead. Long ago, 30 years ago, Ilan Rimon, now a professor at Technion, worked in my group and showed that you could achieve navigation in the horizontal plane purely reactively if you knew everything about the environment, that is the obstacles. And he showed this by reducing geometrically complicated obstacles to their topological models, sphere worlds as he called them. And that gave you a completely general approach to horizontal plane point particle navigation. Now, these ideas were taken up again by another recent student of mine, Ömer Arslan, now professor at Eindhoven University. And Ömer said, let's assume that we know nothing about the environment except that it's this topological model space that Elon had talked about. It's a sphere world, and the obstacles are completely unknown, but we know that they're going to be disks. What Ömer did was he said, let's put a local free workspace around the robot using Voronoi cells. Let's put a metric projection. Let's look at the point on that Voronoi cell that's closest to the goal, paint it red, and let's start sliding the point particle toward that local free space goal. Of course, as the robot begins to move, its Voronoi cell has to move. And what Ömer was able to show was that you get a basin of attraction that's almost global. It's as global as the topology will allow, down to the goal from almost any initial condition on the plane. Well, Vasilopoulos, a recent doctoral student who just graduated from my group, has been able to show that these ideas can be then combined with Elon's ideas by introducing Elon's diffeomorphisms on the fly. Namely, what Vasilis is doing is he'll assume that we have some learned family of furniture, chairs, tables, objects in the world, and we have a sensor footprint depicted in orange in this movie. And as soon as we encounter a known obstacle in the sensor footprint, we can immediately instantiate it into this picture of the semantic space in the second to the left. Things that we've never seen before, we'll just assume are convex in the sense that Ömer would have assumed them to be convex. And what Vasilis shows, as is depicted in this simulation, is that one consolidates the semantic obstacles into their footprint as topological spheres, and then using the known footprint from the learning, even though we knew nothing about their location in the beginning, using that known footprint, we can deform them on the fly into the model space. And once in the model space, we can then use the methods that Ömer developed to have a good energy basin that goes low at the desired goal and goes high at the bad obstacles in the model space. Here, of course, we have to use a hybrid dynamical system because each time the constellation of perceived objects in the sensor footprint changes, the model space has to change. And so it's a little bit of effort to show that this converges, but using a combination of ideas going back to Elon, using conjugacy, going forward to Ömer, using these hybrid systems ideas, Vasilis is able to show that you get convergence from everywhere, even though you don't know anything about the location of the objects to start with. So Vasilis has moved ahead and built a more increasingly general purpose architecture with colleagues, collaborators, some in Nick Roy's group at MIT, some with Yanis Kantaras and George Pappas' group at Penn. And we've been doing increasingly out of scope, more complicated, logically more interesting versions of these navigational tasks using physical robots. But the idea that I want to get across in this talk is that we need to instantiate these point particle dynamics, not simply with these unicycle-like differential drive robots, but we want to move out of doors. And in order to move out of doors, we're going to have to instantiate these horizontal plane dynamics with much more interesting machines that live in the sagittal plane in a very important way. So here's the Ghost Robotics Spirit robot using its sagittal plane compositions that I'm going to describe to you in order to instantiate the differential drive dynamics of the left-hand rolling robot that in turn is instantiating through this hierarchical composition the point particle dynamics that Vasilis's architecture guarantees will converge. So I won't go there in this discussion, but one can imagine doing much more complicated ideas with topology by thinking about the configuration space of multiple particles. Those ideas have been empirically demonstrated. This is collaborative work with Nick Roy, and increasingly complicated mobile manipulation tasks are being done in this way with the same hierarchical arrangement of horizontal plane and even 2.5D tasks of mobile manipulation being translated down through the hierarchy into the sagittal plane. So what I'd like to do is I'd like to now turn attention to that sagittal plane, but before I do that, I want to go back to Professor Simon's idea that you really understand the way in which a synthetic system works by positing an environment and understanding the way in which that architecture will perform that task in that environment. Here's work by Aaron Johnson. He a doctoral student in my group, formerly, who's now professor at Carnegie Mellon, who studied carefully the sagittal plane environment of a leaping machine. And what he came to understand was that it was sufficient for him to characterize the contact points between the environment and the important features of the robot. So here is a setting where there are no legs and no parts of the body touching the substrate. Here is a configuration where there's one leg, either the rear leg or the foreleg, touching the substrate. Here are configurations where only the nose or the butt is touching the substrate. Here are configurations where both legs are touching, and so on and so forth. What Aaron was able to realize was that the relationships between the contacts of the substrate could be organized according to the simplicio complex, another construct from topology. And if you took the adjacency relationship seriously, you could begin to think about the Hasse diagram and navigating up the Hasse diagram, which he did as a human being. He tuned the various configurations of the robot in various positions up this Hasse diagram to achieve leaping in a completely open loop manner, but an open loop manner that he understood dynamically well enough to be able to achieve as a human very sophisticated dynamical maneuvers. I'll spare you the human learning that Aaron went through in order to be able to develop these open loop schemes. But you know, he's a brilliant designer and a brilliant roboticist. I want to then flash forward to the next set of ideas, which have to do with how now to make use of compositions that are going to be producing architectures that work in these environments. Here I want to go back to a notion of hierarchical composition that emerged from Martin Buehler's work. Martin was a student of mine way back in the late 80s, early 90s, and we were inspired to take Mark Rabert's hopping robots and instantiate them in juggling machines. Again, move forward another 5 years or so, and here's Bill Schwinn's work where we're taking that same Rabert pogo stick. It's the white machine embedded in this 4-degree of freedom red machine. The pogo stick has 2 degrees of freedom. The ankle, knee, hip actuated leg here has 4 degrees of mechanical freedom. But whether you adopt a more upright posture or more crouched posture, there he was able to control the position and velocities of the hopping red machine by reference to what we call an anchored template of the Rabert white hopper in that machine. Martin then came back and worked with a different doctoral student of mine, Ulrich Ranli, who's a professor at METÜ right now in Turkey, to build Rex, and Rex empirically anchored the same pogo stick, and it was the first legged machine to ever run outside the physical world unplugged. Okay, so these hierarchical compositions were more or less one-off ad hoc until Avik Dey's work. Avik Dey recently graduated from my group, and what Avik was able to show that you could recover Rayberg's ideas of parallel compositions, wherein the controllers don't know anything about the coupled dynamics of the body, but if you arrange them to not worry about the good crosstalking, if you have to cancel out the inimical bad crosstalk, then you're able to get these successful, provably correct parallel compositions of vertical hoppers, and then in parallel compose them with things like a McGear-style reaction wheel. And so with these parallel compositions that have provable properties, you can now achieve the anchoring of lower degree of freedom subsystems in these high degree of freedom mechanisms. This idea about parallel composition has been embraced by my present student, Turner Topping, first using open loop compositions sequenced according to his own robo-whispering skills. He's a very, very substantially talented robo-whisperer, to be able to get very interesting transitional and steady state compositions. But what I'd like to do, I'd like to now go back to not just the sequence transition, but the notion of a sequential composition that emerged from work that Rob Burge did with Al Rizzi, then in my group, now in Boston Dynamics, to achieve formally composable sequences of what will come out to be hierarchical, parallel achieved hierarchical compositions. And that's where I'm going next. Okay, so let's now talk about how Turner is systematically using these provable pieces, these hierarchical parallel and sequential compositions, to get increasingly provable but empirically worthy compositions. Let's just look at his work where he's doing an ascent up the energy barrier here. And I'm going to spare you the analysis of this thing, but what he's doing is he's using the environmental representation coming from Aaron Johnson together with the compositional notions that Ovid Day gave us to plan a sequence up the Hasse diagram. And he plans the sequence using a variety of these sequences of parallel compositions. He has the beginnings of a programming language. And what I'm trying to show you with this graph briefly is that these are all closed loop now. They're all, there's no more robo whispering going on after you write these quote programs, unquote. You get very, very reliable, very repeatable, highly dynamic transitional maneuvers of a kind that we've never been able to get before. And I'll come back to this idea about universal and edge triggered templates very, very shortly. The idea here, again, coming out of Avic's work, was that you could achieve essentially a universal decomposition of what's called the floating torso model by recourse to the same palette of templates that Turner had begun to use informally. So think about inverted pendula and hanging pendula, and then think about the torso, the body, either pitch regulated to be steady or pitch regulated to be the desired velocity that you want. Avic's work gives Turner the ability to command these completely independently. And so we get a parallel composition table of pogo stick and body that enables him, for example, to program height and a pitch velocity that gives a 270-degree flip, or a different pitch and velocity that would give 360-degree moving along the upper left-hand corner of that palette of compositions. Or if you wanted to do monkey bar work, he has these brachiating schemes where if you've got a very, very long gap, then you want to pitch your body so as to get better gap crossing. On the other hand, if you're fortunate and the runs are close together, then you may desire instead to keep your pitch steady in the lead, so that, for example, your perceptual apparatus would be have an easier time in the sensation. So here's Turner's use of these compositions to achieve a gap crossing where the body can be held in pitch steady mode. So we're now beginning to be able to sequence these parallel compositions that through these hierarchies, again, to get very, very consistent, repeatable, complicated, increasingly complicated maneuvers, transitional maneuvers through brachiating and floor locomoting hops. So I am beginning to run out of time. I think I'll finish by giving a sense of some of the recent empirical work that these compositional methods are allowing, and then finishing with a sense of the recent theoretical advances that give me hope that these informal compositional languages actually begin to have formal status that might give us a topologically sound language at work. So if you have good substrate conditions and your initial plan for gap crossing works, that's great. But if the substrate turns out to be slippery and you don't have an alternative plan, you're going to fail. If instead you can replan on the fly and use a different composition to get a different leap, or if the world continues to defy you and the slipping continues and those leaps fail, but you still have a third or fourth plan, you can be actually edge reactive in this ground reaction complex. And these programs can be rewritten on the fly on the basis of the sensory experience of the robot. So, you have to be able to detect the mode, but to deploy the best reachable edge, these compositions have to be instantiated in real time in a matter of milliseconds on the basis of sensory data. And that's where the work of these recompositions is done. On the theoretical side, work by Jared Culbertson, together with some of the collaborators in our group, has shown that you can take these compositions that we get from Rob Burridge and Al Rizzi on the one hand, and Avik Day on the other hand, and you can form what's called a double category of hybrid dynamical systems. And this double category turns out, according to work that has been led by Matt Kvalheim, a postdoc in my group, working together with Paul Gustafsson, that these double categories that have the formal properties I'll shortly describe indeed have a Conley theorem attached to them. And so you're guaranteed to get a vertical notion of morphism, you're guaranteed to get a horizontal notion of morphism, and you're able to pull out of this thing a hierarchical composition. When you put these categorical ideas together, by the way, the parallel compositions are so a bit rough right now. When you put the category theoretic ideas together, you get what's called a type theory. And this type theory looks like it's going to be able to give us a formalized version of the kind of languages that Turner has been using more informally with the formal, topologically formal compositions that were bequeathed him by Avik and people who've come before. Okay, so I've tried to give you a very cursory view through a case study, if you will, of the way in which topology gives us symbols that have formal properties, which symbols admit compositions, which compositions can also be endowed with formal properties that give enough structure as to promise a programming language using basings as the symbols that have an operational semantics and the physical hardware of the working machines. Thank you very much for your attention in this talk. It's now my great pleasure to introduce the next speaker in this series, Professor Alin Algün Schäfer. Thank you very, very much for your attention.